If I told you there might be a black hole lurking in our cosmic neighborhood, close enough in astronomical terms to be considered nearby, you'd probably imagine chaos. Stars getting shredded, planets flung like marbles, the sky doing something noticeable. But what if I told you the weirdest part isn't that it's near Earth? The weirdest part is that, according to everything we think we know, this black hole shouldn't exist there at all. So, how do you hide a gravity monster next door? And why does its address break the rules? Let's set the scale, because space loves messing with our intuition. Near Earth doesn't mean behind the moon, obviously. It means inside our broader stellar neighborhood, within a few thousand light years, close enough that astronomers can study its effects in detail instead of just guessing from across the galaxy. Now here's the problem. Black holes don't usually just show up. To make one, you typically need a very massive star, something like 20 times the mass of the sun or more, to live fast, die violently, and collapse into a black hole. And those massive stars, they're drama. They blast intense radiation, blow strong stellar winds, and most importantly, they rarely live long enough to drift quietly into the kind of calm, ordinary region of space where we find us. So when scientists identify a black hole candidate that's both nearby and strangely quiet, no bright X-ray fireworks, no screaming accretion disk, alarm bells go off, because that suggests one of two things. Either we've misunderstood what's there, or we've misunderstood how black holes are born and where they can hide. And the story of how we found these impossible black holes is honestly one of the sneakiest detective stories in modern astronomy. The invisible black hole problem. Here's the first twist. Black holes are, by definition, dark. If a black hole is just sitting there, not actively eating anything, it's basically invisible. Most black holes we've confirmed are found the loud way, by catching them in the act of feeding. Gas spirals in, heats up to millions of degrees, and blasts X-rays across space. Astronomers point an X-ray telescope at the sky, see a beacon, and go, "Yep, something extreme is happening there." But a black hole that isn't feeding? That's like trying to find a burglar who never breaks a window, never trips an alarm, and never leaves footprints. So how do you catch it? You look for what it does to other objects, specifically stars. If a star is orbiting something massive, something it can't see, its motion gives the game away. Think of it like watching someone dance with an invisible partner. The partner might be hidden, but the spins and steps still betray the weight and presence of whoever's holding their hand. Astronomers use a few tools for this. One is the Doppler effect. If a star moves toward us, its light shifts slightly bluer. If it moves away, slightly redder. That wobble over time reveals it's orbiting something. And if you can measure the orbit precisely enough, you can calculate the mass of the invisible object. If that mass is too big to be a planet, too big to be a normal star, and there's no light coming from it, congratulations, you might have found a black hole. The nearby candidate. That started arguments. Over the last few years, several nearby black hole candidates have triggered exactly this kind of debate. One especially famous case involved a system first announced as the nearest known black hole to Earth, only for other teams to challenge whether it was actually a black hole at all. And that controversy matters because it reveals something bigger. Confirming a quiet black hole is hard, painfully hard. A system might look like a black hole on first calculation, because the visible star's orbit suggests an invisible companion with a few solar masses. But then someone else rechecks the data and says, hold on, that star's properties were mismeasured. Or, your distance estimate is off. Or, that invisible object could be a pair of dim stars instead. This is astronomy at its most humbling. You're trying to weigh an invisible object from thousands of light years away using tiny shifts in starlight. Tiny shifts, the kind that can be messed up by star spots, stellar winds, or even subtle biases in how data is processed. So when a candidate survives that kind of scrutiny, when the wobble, the orbit, the mass estimate, the lack of emitted light all line up, that's when things get serious. Because then you're left with the question, why is there a black hole there? This black hole shouldn't be here. Okay, what does shouldn't exist near Earth actually mean? It's not that black holes can't physically be close. Space is huge. Statistically, there should be black holes in our region. The Milky Way likely contains millions of stellar mass black holes. Most are just dark. The real issue is this: to produce a black hole, you need a massive star. Massive stars tend to form in dense, active star-forming regions, big clusters packed with other massive stars. Those environments are messy, and they don't stay stable for long. The biggest stars die quickly, and their supernovae stir the neighborhood like grenades going off in a crowded room. Over time, clusters disperse, stars drift, and the whole structure changes. So for a black hole to be sitting in a relatively ordinary, nearby part of the galaxy, a few things have to happen. 1. A massive star had to form in or pass through our broader neighborhood. 2. It had to collapse into a black hole. 3. That black hole had to remain gravitationally bound to the region instead of being kicked away by the violence of its own birth. And that third point is where things get really weird, because black holes aren't always born gently. When a star collapses, especially if it explodes as a supernova, the explosion is often asymmetrical, not perfectly spherical. That means the newborn compact object can get a recoil kick, like a cannon firing a cannonball. Neutron stars are famous for this. They can be launched at hundreds of kilometers per second. If black holes get similar kicks, many of them should be flung far from where they formed. Some might even be kicked out of the galaxy entirely. So if we find a black hole nearby that seems to be moving calmly with local stars, almost like it was born in place, it suggests one of two things. Either it formed in a surprisingly quiet collapse with little to no kick, or it has a history we don't understand yet. The dark birth possibility. Now we get to one of the most chilling ideas in stellar evolution, the failed supernova. Sometimes a massive star might not explode in a bright, obvious supernova. Instead, it could collapse directly into a black hole, quietly. No dramatic blast, no fireworks visible across the galaxy, just lights out. Astronomers have actually hunted for this by monitoring galaxies and watching massive stars over time. The idea is simple and eerie. If a giant star is there one year and just gone the next, no supernova, then maybe it collapsed straight into a black hole. If direct collapse black holes are common, that changes everything, because it means black holes can be born without the violent asymmetrical explosion that gives them big kicks. They'd stay closer to home. They'd blend into the stellar population, and we might be surrounded by more of them than we ever guessed. But there's another problem. If a star collapses directly, what happens to its outer layers? Some models predict a faint brief signal. Others predict almost nothing, meaning the universe could be manufacturing black holes quietly, and we'd barely notice. So when we spot a quiet black hole candidate near Earth, it starts to look less like an oddball and more like a clue, maybe even evidence, that dark births happen. The even stranger option, it didn't form like a normal star at all. And now we go from unsettling to, wait, what? There's a more exotic possibility people whisper about when they say, this black hole shouldn't exist here. What if it isn't a typical stellar collapse black hole? In theory, the early universe could have produced black holes long before stars existed. So-called primordial black holes formed from density fluctuations just after the Big Bang. These wouldn't need a giant star at all. They could be ancient, small, and drifting through the galaxy like invisible bullets. Now, I'm not saying that's what we're dealing with. This is speculative, and the evidence for primordial black holes remains uncertain. But here's why people bring it up. Because if you find a black hole with properties that don't match a normal stellar origin, wrong mass range, wrong environment, wrong motion, then you have to at least ask the uncomfortable question: are we looking at a black hole with a completely different origin story? And even if primordial black holes aren't the answer, the mere fact that the question comes up tells you how much these nearby, quiet black holes mess with our expectations. Why we didn't notice it sooner. At this point, you might be thinking, okay, if there's a black hole nearby, why didn't we figure this out earlier? Because astronomy used to be biased toward bright things. For decades, our instruments naturally detected the loudest objects: stars, exploding supernovae, galaxies blazing with radiation. Quiet black holes don't announce themselves. They don't shine. They don't send postcards. What changed is precision measurement. Modern sky surveys, especially missions that measure star positions and motions incredibly accurately, have turned the galaxy into a motion map. Instead of just photographing where stars are, we can track how they move. That means we can spot wobbles, odd accelerations, and orbital dances that point to hidden mass. In other words, we're finally getting good at finding the invisible. And that means the next few years could be a cascade of discoveries. Not just one nearby black hole, potentially dozens, hundreds, maybe more, depending on how calm and quiet black holes really are. So why does this black hole shouldn't exist near Earth? Because the black holes we're used to finding are the messy, obvious ones. The ones born in violent neighborhoods, feeding loudly, shining in X-rays like cosmic sirens. A nearby black hole that's quiet, dark, and seemingly sitting in a relatively normal stellar environment forces an uncomfortable realization. The universe may be full of black holes we've systematically missed. And if some of them formed through quiet, direct collapse, no bright supernova, no big kick, then our mental map of the Milky Way is incomplete. We've been walking through a city at night with a flashlight, assuming that anything we don't illuminate isn't there. But it is. Now, to be clear, a nearby black hole isn't automatically a threat. Space is enormous, and near still means mind-boggling distances. The danger isn't that it's about to suck in the solar system like a vacuum cleaner. Black holes don't work like that. The danger is conceptual. Because once you accept that black holes can hide in plain sight, you have to ask, how many are out there? How many passed through our region millions of years ago? How many are paired with stars we can see right now, tugging gently, silently, leaving only a gravitational fingerprint? And the final twist? The more precisely we map the motions of nearby stars, the more likely it is that this impossible black hole won't stay special. It'll be the first one we noticed, not the only one. A black hole near Earth shouldn't exist, only because our expectations were built on what's easiest to see: explosions, bright disks, cosmic chaos. But the universe doesn't care what's convenient for our telescopes. It builds monsters in silence, hides them in darkness, and leaves us to notice them only by the way they bend everything around them. And if that's true, then the scariest part isn't that there's a black hole nearby. It's that we're finally learning how many invisible things have been there all along.